All right, I'm back, and I left off talking. All right, I'm back here, and I left off talking about an introduction of ways to control for confounding or to actually prevent it. So 3 strategies for prevention is randomization, restriction, and matching. And I will start first talking about randomization. And randomization is an attempt to ensure equal distributions of the confounding variable in each exposure category. You have a scenario where you are able to randomize the individuals that will be participating in a particular study. And the way you would do that, and I asked this question, how would you randomize for smoking, body weight, and lung cancer, or within that lung cancer study? And so I know a way that you would go about that is, first of all, it's really important to actually have a large sample size. And from there, you are able to randomize individuals based on, or categorize individuals based on whether they're smokers, and then differences in body weight, and then to look from there at their risk for developing cancer. So the advantage of randomization is that it's convenient and inexpensive, and it actually allows for a straightforward data analysis. But the disadvantage is that you need to have control over the exposure and the ability to assign those subjects, or whether they're going to participate in the control group or that intervention. And so that's how you would go about randomizing individuals within your particular study. Restriction is actually, as the word states, is that you actually are going to prohibit variation of the confounder in the study groups. For example, you will restrict individuals or participants to a narrow age category, where you can eliminate age as a confounder. So as many of you know, if you were to do like a cancer type study, they would only allow individuals within a specific age category. Another way that you can look at prohibiting variation with the obesity and smoking with respect to lung cancer is you would restrict individuals, maybe based on smoking patterns or based on obesity or body weight. From that, prohibit individuals, and so at that point you're able to do a study just based on individuals that may be obese or less obese or normal weight that are not smokers in both categories. So it actually provides complete control of the known confounders. The disadvantage is that unlike randomization, you cannot control for unknown confounders, and ultimately it may shrink that pool of subjects to an unacceptable level. So like with the obesity and smoking, if you start with 100 individuals and you want individuals that are obese or normal weight, but then you have to eliminate all those individuals that smoke. Instead of starting with 100 individuals, you may be down to only 70. And then you break it into body weight categories, and you may have a pool of subjects that just may be too small. As well as when you restrict, the findings may not be generalizable, as in your study is so narrow-minded in the sense that it's only individuals that are at this specific body weight or under this body weight that are not smokers. And so at that point, you may not be able to take the data and move and generalize it to a larger population. All right, and then the third way to actually control for confounding or prevent it is through matching. And if you may recall in one of the exams with the toe cancer examples, we actually had a matched case control study where we matched subjects in the study groups according to the value of the suspected or known confounding variable to ensure equal distributions. And so, for example, with the lung cancer and the obesity and smoking, you can match individuals based on, if you're going to be looking at smoking versus non-smoking, you can match the same body weight individuals. You can take one individual that has a similar BMI in the smoking category, and then you match that with an individual that has the same BMI in the non-smoking category. And so there's ways to do matching by way of frequency matching, the number of cases within a particular match characteristic where you tabulate that, or as I just provided an example of individual matching, where the pairing of one or more controls to each case is based on similarities such as sex, race, or other variables. The advantages to matching is that it only requires fewer subjects, and you don't eliminate individuals as you would if you did restriction. And so an example that I provided here would be doing a renal cancer case control study where you only have few individuals that are able to participate in that because there's already few people that you would be able to identify that have renal cancer. And you can match those controls based on age, race, sex, and neighborhood. So you take an individual that has renal cancer and then you match those characteristics of that individual that has the cancer and find an individual, a control that has a similar age, similar race, similar sex in the same neighborhood. And it allows for the potential for validity of a follow-up study. The challenge, though, the disadvantage is that it is costly because you have to actually go out and find those individuals and keep those records of those matched individuals. And then the other thing, too, is that it may introduce confounding factors rather than controlling for that. All right, so the methods that we just already talked about in the previous slides are with restriction, with randomization, and with matching are ways to prevent or reduce the potential for having confounding variables within your study. But that being said, ideally, you want to be able to control for them, but it may not be costly or feasible to actually address all of those in the initial design of the study. And so at that point, as well as there are additional confounders that you may not have taken into or not observed in the initial design of the study, and you detect them at the point of analysis. So that it comes up, whereas how do you actually control for confounding variables on an analytical side? So there's ways to prevent it, and then there's ways of just dealing with confounding variables within the analysis. So there's two strategies to actually control for confounding in the analysis portion. And one is stratification, where there's an analysis that's performed to evaluate the effect of an exposure within different strata of the confounder. And then there's multivariate techniques, where I'm only going to briefly introduce, where there's whole computer models as well as mathematical models that simultaneously describe as well as analyze the exposure and other factors. It kind of builds into this the multiple confounders that may be present. All right, as I just introduced a second ago, stratification, and I want to talk a little bit more detail about this. It evaluates the effect of an exposure with levels or strata of the confounder, and it defines homogeneous categories or narrow ranges of the confounding variable. Basically, you're breaking things down into smaller and smaller categories, and then you do the analysis. So an example of stratification that I have been involved in is, if many of you recall, I did an HIV study here in the state of Utah, and one of the confounding variables that we had to look at was at age, and how age of the patient or age of the individual that was HIV positive could potentially play a role or be a confounding variable. And so the way that we dealt with this within our analysis is that we actually stratified our age groups. So it wasn't like we looked at all individual, we did initially look at all individuals in the state of Utah, but we broke each category down based on different age groupings from children to teenagers to young adults to older individuals. And from that, as you do these stratum-specific categories, you're able to actually start to see the effects of confounding variables on these different strata. So the advantage of this, of stratification, is that it's after the fact. You can actually do analysis within those strata and actually have direct and logical strategy or make assumptions based on the data that you're analyzing. Another advantage is that minimum assumptions must be satisfied for the analysis to be appropriate, as in you're able to stratify, but you don't have to make any assumptions initially when you look at the analysis. And the computational procedure on how to stratify is actually straightforward, and you can develop that strata based on different criteria that are already established within the scientific community and the statistical community. The disadvantage of stratification is that oftentimes small observations will ultimately occur within different strata, and that's what we ended up having, is that we stratified with our HIV study into so many age grouping categories that it became we found statistical significance in some of these really small groups. And so what happened is that the reviewers of the manuscripts basically said you're making too much of your findings because your numbers within each strata are too small. And so the recommendation is that we had to combine some of our strata or make those age groupings larger. Also, another disadvantage is there's a variety of ways to form strata with continuous variables, and it's oftentimes when you have those different ways, it's difficult to actually interpret when you have all these different confounding variables and how to actually analyze them. So, lastly is that categorization produces loss of information, and you end up potentially losing some of those real neat findings that can come when you do these, when you stratify the data. But it is an important tool. It's a very important tool when it comes to dealing with confounding variables. So the last technique that's out there that I wanted to talk about, it's not a last technique, but it is a very important technique for dealing with or being able to analyze confounding variables, is a multivariate technique. And this is where computers are used to construct mathematical models that describe the influences. It allows you also with multivariate technique to use continuous variables. It's not a yes or no category, as in you could, with blood pressure, for example, you're able to actually analyze the data across that continuum. And the programs that are used out there allows for you to develop or to establish cut points, but be able to move those cut points in order to look at that confounding variable and the analysis and those findings. The advantage behind these techniques is that continuous variables, as it says, do not need to be converted to categorical variables, and it allows for simultaneous control over several exposure. But the challenge, though, is that the use of multivariate techniques in these computer programs allow for the potential for misuse. You can make more of it than it actually is. And often people don't understand the different models that are out there when you read the literature and misapply those techniques. Now, in this course, all I do is introduce that there are computer programs to look at more than one confounding variable, but I don't expect you to know how to do those as if you do need to understand them when it comes to stratification. All right, I'm going to change topics just for a minute here and talk about publication bias. This is another aspect that's very important, and this occurs because the influence of study results do ultimately influence the chance of publication. Studies with positive results are more likely to be published than studies with negative results. It's kind of this chain reaction that we do see within the literature. A personal example of mine is that I had a paper that ultimately was published looking at mosquito evolution, but we submitted it at the same time as another researcher. This particular researcher actually sat on the review panel of this particular journal, did not know that, and ultimately the paper was rejected because it was counteracted this particular individual's findings. As I said, it was ultimately published at another journal, but that was kind of an example of publication bias. It also may result in the preponderance of false positive results in the literature, where positive results are more likely to be published, and often they build on each other. So the biases could be confounded when there's meta-analysis. Meta-analysis is where there's a study that actually analyzes many studies. And so it's something that you need to be aware of when you're reading literature, and you always need to take a step back and really kind of analyze the data that's out there. All right, that's the end of Chapter 10. If you have questions, we can talk about them in class, or you can send me emails. Thanks a lot.